So in 3.7, we revisit this idea of implicit differentiation that we talked about last year in AB calculus. So if we have a function y squared equals x, when it's written this way, where we have not solved for y by itself, we would say solving for y explicitly, then this represents an implicit function of y. That is, we still assume here that y is a function of x, even though we haven't solved for it, and then sometimes where it's not even possible to solve for it. But we'll talk about still that we can find the derivative even if we can't write it explicitly. Now in this particular example we can. So when we solve for y and write it explicitly, we see it's actually representing two different functions. Y equals the square root of x and y equals the negative square root of x. So that's like the top half of a sideways parabola and the bottom half of a sideways parabola. So we're going to find the slope of the tangent lines. Notice it's plural because there's going to be one for each of those functions at x equals 4. And then we'll come back and do the problem using what we'll call implicit differentiation. So looking at our first function, say positive x to the 1/2, then we know that its derivative is going to be 1/2 x to the negative 1/2, which is 1 over 2 square root of x. So if we evaluate that at x equals 4, then we are going to get 1 over 2 square root of 4, which is 1/4. So that's the slope of the tangent line to that first curve at x equals 4. Then looking at the second function, the y equals negative x to the 1/2, then its derivative, dy dx, will be a negative 1/2 x to the negative 1/2, which is a negative 1 over 2 square root of x. And when we evaluate that at 4, we'll get a negative 1 over 2 square root of 4, which is a negative 1/4. And that would be the slope of that second tangent line. Okay, now just to make sure we're clear, we could do this same problem but using what we call implicit differentiation. So without trying to solve for y, we can differentiate this with respect to x. And so we have to remember that we're treating y now as some unknown function of x. And so when we try to differentiate y squared, we have to use the chain rule. So we take 2 times the y to the first, and then times the derivative, and maybe that's unfortunate notation. I'm going to just leave that as y to the first, times the derivative of the inside function, that y, which we don't know what that is explicitly. So the best I can do is just call that y prime, representing the derivative of that unknown function y. And the derivative of x we still know is 1. So from here we can solve for that y prime, and so when we divide that 2y to the other side, we get that y prime is 1 over 2y. So we could still now solve for this at x equals 4 is what we said. But now what we have to do is come back to here to solve for what is y when x is equal to 4. And here is where we're going to get, it can be either a positive or a negative 2. And so that's how we're going to get that y prime is, in one case, going to be 1 over 2 times 2. There's our 1/4. And in the other case, it's going to be 1 over 2 times negative 2, which is the negative 1/4. And so we get the same answers either way, and that's supposed to give you some kind of confidence or trust in the process, in the fact that it works. So since we've done some of these before, I'm going to make the huge leap from these very simple ones to ones that are much more complex. So let's look at something like y equals cosine of 2x minus 3y and see how we can find the derivative here. So we want to find, and we could call it dy dx, or we can use our notation y prime is the one that is probably a little simpler. So when we differentiate this, we're going to have to differentiate both sides of this equal sign. So you can see, and maybe we should point out, you can see that this is an implicit function because we have x's and y's that are pretty hopelessly intertwined there. So it's not going to be maybe possible at all, but certainly not easy to try to get y by itself. So that just means we're going to do implicit differentiation instead. So differentiating the derivative of y, we're going to call y prime. The derivative of cosine, here's our chain rule, so it's going to be a negative sine. Leave that inside stuff alone for now. And then we're going to multiply that by the derivative of the inside function, which is going to be the derivative of 2x is 2, and then we'll have a minus 3y prime. Okay, now we see that there are y prime terms in two places, so we need to gather the y prime terms on one side of the equal sign and the non-y prime terms on the other. So first we're going to have to distribute these to separate out the 2 from the 3y prime. So from here we have y prime is equal to, that's going to be a negative 2 sine of 2x minus 3y. And then we're going to get the negative 3 times the negative in front of the sign. We'll make that a plus 3y prime sine of 2x minus 3y. So now we're making progress. We have our two terms that have y prime in them. So I'm going to move those to the same side. So you can go either way, but I'm going to subtract the 3y prime term to the other side. So that's going to make that y prime minus 3y prime sine of 2x minus 3y, and that's leaving on the other side that negative 2 sine of 2x minus 3y. So finally now on the left side we can factor out that y prime, leaving the 1 minus 3 sine of 2x minus 3y, still equal to that other stuff. And then we can divide to solve for the y prime, so it looks a little messy, maybe even a lot messy, but our claim is that the derivative is going to be what we see coming out of this. Now it may be tempting to try to cancel those sine of 2x minus 3y's. Resist that temptation, because that is not correct. Because of the 1 minus, we can't just cancel an individual term. I'm going to go to a new panel here. And let's try another one. So let's see, we have e to the x plus y is equal to, let's say, e to the xy, and then minus e to the 2y, and again we're going to try to find y prime, the derivative. So we're going to differentiate here through both sides of the equal sign. Whoops, I didn't do that very well. So we're going to differentiate there. So when we take the derivative of e to the x plus y, we're thinking of that as e to the u times du, the derivative of that exponent, which is going to be a 1 plus y prime. In the next term, again, we're going to get e to the u du, so we get the same exponential e to the u. This time the derivative of the exponent is a product rule. So it's the first times the derivative of the second plus the second times the derivative of the first. And then finally, we're going to get an e to the du here, so it's the same exponential, negative e to the 2y, times the derivative of 2y, which is going to be 2y prime. So on the left side, we're going to distribute our exponential. So that's going to give us e to the x plus y plus y prime e to the x plus y. So we can see on that left side, we have one term without a y prime and one term with. Eventually, they're going to have to go to different sides of the equal sign. Similarly, we're going to get x, y prime, e to the xy, and then a plus y times e to the xy. So another, again, one term with y prime, one without. And here we're going to get a minus 2y prime e to the 2y, and that has a y prime in it as well. So I think because we have two of the y prime terms on the right side, I'm going to move that one on the left side to join them. So it looks like we have an x, y prime, e to the xy, minus 2y prime, e to the 2y, and then minus the y prime, e to the x plus y that we moved over. On the left side, we're leaving that e to the x plus y, and we're going to move over to join that, the term that doesn't have y prime on the right side, so that'll be a minus y e to the xy. So on that right side, we're going to isolate our y prime by factoring it out. That will leave behind x e to the xy minus 2e to the 2y minus e to the x plus y. And the left side's just hanging out, waiting for us to divide over here on the right. So finally, we're going to divide that whole mess over, which is not, I agree, terribly pretty or inspiring, but nonetheless, I believe this is what we want for our derivative. There we go. Okay, let's do one more and we'll talk about these ideas of slope and concavity. So let's say find the slope and concavity, that is it going to be concave up or concave down, of our implicit function x squared y plus y to the fourth equal to 4 plus 2x at the point -1 and 1. So first the slope part. So when we're looking for slope, we want to find the derivative. So differentiating here, we're going to first do a product rule on that term. So there's the first times the derivative of the second, plus the second times the derivative of the first. Then we have a chain rule derivative on the y to the fourth. So that'll be 4y to the third times y prime, the derivative of the inside function. On the right side, the derivative of 4 is 0, and the derivative of 2x is just 2. So we can go ahead now and evaluate this at x, y equal to -1, 1. And so that means we're going to get, let's see, x is -1, so that's going to be a -1 squared y prime, and then plus 2 times -1 times +1, that's the 2xy, plus 4 times 1 cubed is 1, and another y prime that we're working towards finding, and that's equal to 2. So that looks like 1 y prime there, and that'll be a -2, and then a 4y prime there equal to 2. So I think that's 5y prime. Adding the 2 over makes that a 4, so y prime is going to be 4/5, and that is our slope. So here is the slope of our curve at the point -1, 1. So now we're ready to talk concavity. So now we're going to take this answer that we had for the first derivative, and we're going to come through and differentiate it again. Do I want to do that? I think so. So let's see if we can do this. We got a product rule right here. So we're going to have x squared, the first, times the derivative of the second is going to be, there's our y double prime, plus the second, which is y prime, times the derivative of the first, which is a 2x. And then another product rule is going to be the 2x times y prime plus 2 times y. That is y times the derivative of 2x. We have yet another product rule. So we have the 4y to the third times y double prime. And then we have our y prime times, that's going to be 12y squared times another y prime from the derivative of the inside function, and that's going to be a 0. Now remember, we're trying to find concavity, so we don't have to actually solve for y double prime. We can just start plugging in these numbers here. So we were still at the same point. That's going to be our negative 1, 1. And we know that y prime is equal to 4/5. So x squared is going to be negative 1 squared. Y double prime is what we're trying to figure out. Y prime, we said, is 4/5, and 2 times x, which is negative 1, is going to make that be a negative 2. Plus, we have 2 times negative 1 times 4/5 is the y prime, plus 2 times 1, plus 4 times 1 cubed is 1, times there's another y double prime, plus y prime, which is again 4/5, times 12, and times y squared, which is 1, and times y prime, which is 4/5, is equal to 0. Yuck. So it looks like we have a y double prime here. It looks like a minus 8/5 from that next term. And I think here we're going to get another negative 8/5. And then a plus 2. And then a plus 4y double prime. And now let's see, we've got 12 times 4 is 48. 48 times 4, I think, is 160 plus 32, 192. Hope I did that right. 5 squared on the bottom is 25. Yuck. Okay. So the two y prime terms combine to be 5y double prime. And on the other side, we're going to get, let's see, our negative 8/5 and another 8/5 makes negative 16/5. Adding that to the other side is positive 16/5. We're going to have to subtract that 2 and subtract the 192 25ths. So I'm going for the easy way out here. So I think what we have is, if we get a common denominator of 5, if we multiply top and bottom by 5 on the 16/5, 5 times 16 is 80 25ths, and the negative 2 would be a negative 50 25ths, and we already have that negative 192 25ths, and we're going to divide by 5 or multiply that whole thing by 1/5. If we're talking concavity, all we really need to know here is, and I think I wrote 2 minus signs, I think that's just a minus. If we are just looking for concavity, all we care about is the sign, and it looks to me like that y double prime is going to be negative. And that's enough for us to conclude that the original function must in fact be concave down. All right, very good. That was pretty fun.